friends, now we will see some hypothesis testing, right? So let's say here we will cover these topic. These are CLT, that is famous, we can say, algorithm, right, which is central limit theorem, and we will see what is point estimation, how the confidence interval works, and what about the hypothesis test for population mean, right? And we will also see one-tailed and two-tailed tests. So as you can see by the topic itself, these are very important topic in terms of statistics and in terms of statistics that is going to be used with our machine learning. So let's start with importing our packages, right? So again, pandas, as we use and used to import it for manipulating and analysis of our data. Then we will import numpy as np, which is used for working with array, right? And then we will see matplotlib again to plot our graphs or visualize them. Then seaborn is also for visualization, and here we will again import our stats, that is the library for the all the statistics work, like probability distribution as well as growing library of statistics function, right? So before wasting the time, let's start with the central limit theorem, that is CLT. So central limit theorem states that if we independently draw multiple samples, right, from a particular population, so we take the mean of each sample and plot these sample that are nothing but these sample means, right? And then the plot will tend to normal distribution as size of sample increases, okay, but regardless of the shape of population distribution. So let's watch CLT, how it work with our Python. Here is we have our uniform distribution, which is most definitely not normal, right? So here we import our uniform distribution from the stat. We import just uniform, and what we are doing is we are seeding the reproducibility, right? So if we are seeding one, so our random number will never get changed, right, once it is created. So create a uniform distribution population of size 1 lakh, and then uniform population, that is uniform.rvs, right? So rvs is nothing but our random variables, right? So from 0 to 10 we want it, and the size of those should be 1 lakh. So visualizing the uniform distribution, we are having histogram, right? So what we'll do is we will make a histogram in that uniform population, and here you can see that we got those numbers from 0 to 10 and which are distributed in 1 lakh distribution. So let's create a sample distribution from this population, okay, and where we have sample size is 5 and number of sample is 500. So what we'll do is we'll draw a sample of size 5, right? So our n will become 5, right? And we will draw 5 independent observation. So first get the mean of these 5 observation, right? That will be nothing but our sample mean, okay? And then we will repeat the 2 steps, because 500 times, so the sample will meet the condition, right? So we get the 500 sample means where n will remain our 5. So let's frame this logic in our program with Python. So you can see that again we are doing random seed for reproducibility, right? And n is our 5. We are having the sample means in our list. Then we will iterate a loop for 500 times to get those 500 sample, right? And each time what we'll do is we will have random of choice of those uniform population where our size is again 5, right? So each time it will keep adding with this list, okay? And then we will calculate the sample mean, right? So this is how the sample mean will be calculated. Later we will append the sample mean to the sample mean list, okay? So here we will get our final sample means. So if we make a this plot for this sample mean, right, where we are again saying that the KDs is also true, and the distribution of sample mean of those 5, right? And here it will look like this. So you can see that it is slightly but not exactly equally distributed. Okay, let's create another sampling distribution from this population and increase the sample size from 15. So here in this case our n will become 15, rest thing will remain same. So if it is 15, so the again you can see that the curve that slightly have changed now in that case, right? If we increase that to 30, so n will become our 30. So here the curve that is we can say approximate the condition for our distribution, but here it should be slightly different. So again if we increase the size to 50, again our n will become 50. So now you can see that our how the sample distribution moves closer to normally, right? So it is slightly closer to the normally as the sample size keep increased. So here if the size is increased, then only we got that normality. Now what it is telling that when the population distribution is normal, so in that case what it will be, so again we are seeding our reproducibility, right? And we are telling that again the same thing, just the population size is 1 lakh and plot a histogram. So here you can see that how our normal distribution will look like, because here we are doing norms.rbs, but remember initially we did as our uniform.rbs. So this is the difference, right? And let's create a sampling distribution from this population where size is 5, number of sample are 500. So draw a sample of size 5, so n will again be our 5, right? And again the condition will remain same. So this time let's see what happens. We are again seeding our reproducibility, and n is our 5, sample mean this, and here you can see now this time we will do it for our sampling distribution. Okay, so here you can see that if the n is our 5, so again how the distribution went, right? And here the insight is when the population distribution is normal, sampling distribution is closer to normal for even the smaller sampling size like n. So here you can see initially we got the slightly equally distribution, right? If again we increase the size of n to 15, so for normal distribution again it will more closer to that curve, right? And if it is 30, so for 30 you can see that how again it is distributed. So let's see if CLT works if the population distribution is exponential distribution, which again is clearly not normal, right? So how it will again look like if we are doing exponential for that RBS. So you can see that the whole thing got changed this time, right? And if the n is 5, the code remains same, only the value will be changed. Okay, because here we will get the value from this exponential population. Here it is. So you can see that here how the slightly distribution got changed, and if it is 15, that means the n is 15, so the curve goes like this. If it is 30, then rest thing will be same, but the n will change. So here you can see that it is quite closer to that, but now what we did is we just increase that up to 50. So here you can see that for 50 it is more closer to that, right? But as compared to this the thing slightly got changed here, right? The curve is 10 to left side right now. So what the takeaway is, we have tried different distribution to simulate the fundamental idea of CLT, right? And we can see that no matter what the shape of population distribution is, the plot of sample mean approximately tend to normal distribution as size increases. So let's see how population mean is estimated by the samples mean. Okay, so what it is saying that let's say a non-profit organization sampled the file of the local forest department to come up with the following amount. Okay, and in thousands of dollars of damages for 10 wildfire incident, and these are these 10 wildfire incident. And what is the estimate of average amount damage in wildfire in that area? So we got our sample size. This is np.array of this number. Okay, and now we will get the mean. of the sample. Okay, so this is our mean. So it is 69%, we can say, the average amount of damage in wildfire. All right, now the insight of this average amount of damage in wildlife is yeah, obviously $69,000. Okay, usually point estimate of an unknown population parameter is the corresponding sample statistics. For example, population mean is estimated by the sample mean. All right, population median is estimated by the sample median, and population proportion of success is estimated by the population proportion of success P. All right, now let's see the confidence interval. Let's see how confidence interval is constructed for the population mean when standard deviation is known. So it is rarely the case when no, you know, the population standard deviation and not the mean, right? That is very rare, and it may not be as unlikely an assumption as it seems. So for tight manufacturing process which is in place for a long time, and the variability in the process may be controlled. Okay, but with small changes in temperature or humidity, the mean may change, obviously. So let's construct the confidence interval for an example where the population mean is unknown and the standard deviation is known. So the caffeine content in mg was examined for a random sample of 50 cups of black coffee dispensed by a new coffee machine. Okay, and the mean of the sample is found to be 110 mg, and it is known that the standard deviation from all the machine of the manufacturer is 7 mg, and construct a 95% confidence interval for that mu, right? And the mean caffeine content for cups dispensed by the machine. So let's try to do that. First, again, we will import our norm for normalization in that stats, and what we are getting is we are setting the value of sample mean and sigma, right, respectively. Then we will define n, and here we will round the norm dot interval, right, up to 95% level. Okay, and scale that with sigma with S scale we get from here. All right, so this is what our array will look like. So what it is trying to say that the 95% of the time the mean caffeine content for cups of coffee dispensed by the machine will be between 108.06 mg and 111.94 mg, right? So let's see how confidence interval is constructed for the population mean when standard deviation is known. Again, we will have the same thing, right? So the above example based on the assumption that the population standard deviation is known. However, in the majority of cases that assumption will not be satisfied. So when we do not know the population standard deviation, it can be estimated from the sample. Okay, so in that case the sample mean follows the student's distribution with n-1 degree of freedom. So this is very important term. We will see that how we'll use that. So just like the normal distribution, t distribution is also very useful in statistical inference, and it is a symmetric distribution around 0 for a very large d and f. That t distribution is almost identical to the standard normal distribution. Okay, and the parameter of this t distribution is known as degree of freedom. So below is the graph of t distribution for various degrees of freedom, and we can notice that the distribution approximate to normal as the value of k increases. So here you can see that this is importing t and this is import normal distribution, right? And here we have defined our x again with that linear space. Figure and axis we are defined separately, right? And where we have said that shear x is false but shear y is also false, and fixed size is 15 by 10. For I in k means there will be plot for each and every single points, right? And here you can see that plot for every these 6 random numbers, right? And here you can see that we are plotting with that t.pdf. T is again our what, stats, right? And probability density function will be for this k, and similarly for this x, right? And then we will get all these. So here you can see that we are, if the color is red, so that is probability density function for our k values, right? All these k values. And if it is red, so it is normal for that x. And here you can see that how all these 6 graph are behaving, and at the last, that means if the size that is increased up to 30, so how it matched with x and our random value. So let's use the t distribution to construct the confidence interval for the mean when population standard deviation is known, right? So the caffeine content in mg was examined for a random sample of 50 cups of black coffee and dispensed by a new machine. So the mean of the sample is found to be 110 mg and the sample standard deviation is estimated to be 7 mg. So construct a 95% confidence interval for mu, the mean caffeine content for cups dispensed by the machine. So here you can see that again the required function t, we are setting the value of sample mean and sample standard deviation, setting the value of sample size and degree of freedom, and here you can see that we are constructing the confidence interval. All right, so it is telling that 95% of the time the mean caffeine content for cup of coffee dispensed by the machine will be between 108.01 mg and 111.99 mg. So what is the key takeaway? So the confidence interval for the population mean can be constructed for both cases when the population standard deviation is known, and when it is known, the later case is more common, which demands the population of t distribution with appropriate degree of freedom. So the general approach to the construction of confidence interval is to use the appropriate sample statistic to estimate the population parameter and use the proper percentile point of the sampling distribution. So let's see now the hypothesis test for population mean. So we will have one sample g test and two sample g test. Let's try to understand the one sample g test first. So it is really the case when you know the population standard deviation, as I mentioned above, and but let's assume that that is the case, right? So it is known from experience that for a certain e-commerce company, the mean delivery time of the product is 5 days, okay, with a standard deviation of 1.3 days. So the new customer service manager of the company is afraid that the company is slipping and collects a random sample of 45 order. So the mean delivery time of these sample come out to be 5.25 days. So is there enough statistical evidence for the manager apprehension that the mean delivery time of product is greater than 5 days? Okay, so use label of significance sigma 0.05. So let's create the null and alternate hypothesis. Let mu be the mean delivery time of the product, and here we will have our h0, that is null hypothesis, and ha, let's assume, which is our alternative hypothesis. So if it is null hypothesis, we are telling that mu is our mean delivery time of the product is 5. If it is alternative hypothesis, so mean delivery time of the product is greater than 5. So are the assumption of z-test satisfied? So let's say sample are drawn from a normal distribution. Since the sample size is 45, which is greater than 30, so the central limit theorem states that the distribution of sample mean will be normal. If the sample size was less than 30, we would have been able to apply z-test on if we knew that the population distribution was normal. But the observation are from a sample random sample. So the observation are from a sample random size. So we are informed that the manager collected a sample random sample, right? So standard deviation is known as yes. So the next step is to find the z-test statistics. Okay, again we will define our mu and sigma, and our sample mean is 5.25 in this case. So if we calculate the test statistics, so here it will be given as this. So the g-test statistics follow a standard normal distribution, right? And let's plot the distribution of the z-test statistics and see where the computed test statistics lies in the plot. So here you can see that we have draw a vertical red line through the mentioned point that are test stats, right? And this is how we got that probability density function for our this normal distribution. Okay, so what is the probability of getting the calculated value of test statistics or bigger in the above distribution? So here you can see that to again calculate them using the CDF function, we will subtract that from 1 and this will get the probability that is 0.98 percentage. So though the probability is very small, is it significant enough to reject the null hypothesis in favor of alternate hypothesis, right? So to do that, we have separately defined that the introduction of rejection acceptance region p-values. So though the probability is small, we cannot conclude whether the evidence is significant enough to reject the null hypothesis, right, in favor of alternate hypothesis or not. To determine it, we use either one of the following approaches. So what we are doing is we can either do rejection region approach and either do p-value approach. So if we talk about rejection region approach, so for this approach we need to follow the below step. What are these? We choose a value of level of significance, okay, then we find the rejection region in the graph, then we reject the null hypothesis if the statistics fall in a region rejection region, right, else we don't reject the null hypothesis. So basically that was the simplest point for that. Now again, how we can do that? We are importing it from stats, that is normal and normalization, and critical value we are getting from norm.pf present point function, right? So 1 minus that value and we will get our critical value here. So the critical value separate the region where we will reject the null hypothesis from the region where we don't reject the null hypothesis. So this is very important point. If we plot that, you can see that we will get that this value that is separated, right? So this is separated by that ppf, and if we plot this, so you can see that first we create an array of 100 numbers starting from -4 to ending 4, then we plotting the PDF of the normal distribution, then drawing a vertical red line through the normal mentioned point, and then creating an array of 50 numbers starting from the critical value and ending at 4, then fill the area under the curve after the critical value with red color and annotate the mentioned text to the mentioned location. So these are the description I was reading that, although you can go with the code only. Okay, so here we will not reject the null hypothesis. Here it is telling that rejection of the null hypothesis. So about insight, as our test statistics nearly 1.29 does not lie in the rejection line. All right, so we cannot reject the null hypothesis here. Thus we do not have statistical evidence to say that the mean delivery time of a product is greater than 5 days. So here you can see that this is the point that is telling that. And p-value approach, the again another approach. So through the rejection region approach gives us the desired discussion. It does not say anything about the strength of the evidence, since statisticians prefer p-value approach, with measures the strength of the evidence against the null hypothesis. So for the approach we need to follow the below steps. We choose a level of significance, then we calculate the p-value. We reject the null hypothesis if p-value is less than equals to alpha, else we fail our rejecting the null hypothesis. So here you can see that if we plot this, it is closer to 1 now, right? So here if we get our p-value using the CDF function, again it is giving us 0.09, right? So as the p-value is near to 0.098 is greater than level of significance, so we cannot reject the null hypothesis here. Thus we do not have statistical evidence to say that the mean delivery time is a product is greater than 5 days. Takeaway here for the key that we get the same result by using both the rejection reason and p-value approach, that the manager does not have any statistical evidence to say that the mean delivery time of a product is greater than 5 days. Now let's move forward with the one tail and two tail tests. As you have might heard about it, these are very important point in terms of statistics. So let's see with an example. Suppose a soft drink manufacturer most selling product is 600 ml, right, and that is Coke with a standard deviation of 50 ml. So a customer would like to test whether there is at least 600 ml Coke in the bottle. So he doubt that the amount of Coke in the bottle is less than 600 ml. So the null hypothesis formed by the customer is 600 now, and again the alternative hypothesis is less than 600. However, the quality control term want to exactly 600 ml Coke in the bottle. So the team want to ensure that the amount of Coke in the bottle is not different from 600 ml, right? So the null hypothesis formed by the quality control team is our 600, and again the alternative hypothesis will not be equals to 600. So the choice of one-sided versus two-sided alternate hypothesis depends on the nature of the problem. Let's see the two-tailed test example. Suppose you work on a quality control team or company, and it is known for from experience that the mean amount of Coke in a bottle is 600 ml with a standard deviation of 50 ml. So you have collected 36 randomly sampled bottles, right? The mean amount of Coke in the 36 sample is 580 ml. So you intend to test whether the amount of Coke in the bottle is different from 600 ml using 0.05 level of significance. So do you have enough statistical evidence for it? Are the assumption of z-test satisfied? So samples are drawn from a random distribution. Since the sample size is 36, which is greater than 30, central limit theorem states that the distribution of sample means will be normal. So if the sample size was less than 30, we would have been able to apply z-test. And if we knew that the population distribution was normal, so observations are from a random sample. So we are informed that you have collected a random sample, and the standard deviation is known as yes. Now the next step is to find the test statistics. So again we are defining our mu and sigma, right, values of those population mean and standard deviation to 650 respectively, setting the value sample mean to 580. Then we calculate the statistics. So here it will return minus 2.4. So let's use the rejoin approach for two-tailed tests, right? So in the given example, the z-test statistics follow standard normal deviation. So the z value laying in the left and right end of distribution gives a strong evidence against the null hypothesis. So to find the rejoin, we will find the values of z called critical values. So the given an area alpha by 2 to both the left hand and right hand side. So here you can see that this is the rejection null and this is the rejected null values, okay, and it is do not reject the null values. So this is distributed like that. If we talk about one-tailed test example, so it is known that the mean amount of Coke is is 600 ml with the standard deviation of 50 ml. So suppose you are a customer who wants to test whether the amount of Coke in the bottle is less than 600 ml, right? So you have collected 36 randomly sampled bottles, and the mean amount of Coke in the 36 sample is 580 ml. So do you have enough statistical evidence for it? Again, are these assumptions of z-test satisfied? So sample are drawn from a normal distribution, right? And since the sample is 36, which is again greater than 30, so CLT states that the distribution of sample means will be normal. So if the sample size was less than 30, we would have been apply z-test, right? And if we knew that the population distribution was normal, so observation are from a random sample, we are informed that you have collected a sample random size. So again the standard deviation is known as we'll have yes. So the next step is to find the test statistic for it as well. Then we will get the minus 2.4 again using the same formula. And if again we use the rejection region approach for one tail test, so here you can see that again we are applying norm.ppf, and if we talk about it only, so this will be our reject null, and this is do not reject the null hypothesis. Last but not the least would as our test statistics in this case lies in the rejection region, right? So we can reject the null hypothesis clearly, and thus we have enough statistical evidence to say that the amount of coke in the bottle is less than from 600. But as you remember that in this case what was happening, we can reject the null hypothesis as well, okay, because it is also lies in the rejection point, and thus we have enough statistical evidence for this case also. So in one-sided test we consider the difference only in one direction. However, in two-sided test we can interest to know the direction of the difference, right? So depending on the nature of the problem we choose accordingly. Thanks.